In this lesson we're going to look at thermal conduction. Now, thermal conduction is the mechanism by which heat is transferred in solids as opposed to liquids or gases, which we'll look at in the next lesson. Okay, so conduction is how heat is transferred in solids. And we learnt in the previous lesson that heat always flows or is transferred from a hot region to a cold region. So where we're heating this metal conducting bar here, what will happen is heat will gradually flow along the bar from hot to cold. But the question is, in this lesson, is how does it do that? Okay, so we need to think about the particle model. What's going on inside the bar? Well, it's a metal. It's made of atoms which are in general very closely packed together. And what we know is that the atoms or particles in all solids are constantly vibrating in all directions and occasionally bumping into each other. And when I start to heat up this iron bar, okay, these atoms are going to start vibrating around more and more, the ones near to the flame. Okay, so, and as they vibrate around more, okay, they're vibrating in all directions, they're going to start colliding with the atoms in their vicinity and causing these atoms to vibrate, okay, and then causing the ones around them to vibrate, okay, and these start vibrating around more, and so on and so on, and gradually these vibrations are transferred along the metal conducting bar as the vibrating atoms hit each other. Okay, so this will carry on so on and so on, and once I remove the heat source, okay, these vibrations will gradually continue to move from the hot region to the cold region until they're all basically moving with the same average kinetic energy. That's to say the bar is in thermal equilibrium, or the temperature in the bar is the same right the way along its length. Okay, so heat is transferred in a metal conductor as the vibrating atoms collide with each other and transfer those vibrations throughout its structure. Okay, so what happens then when a material is not a good conductor following this model? For example, as we learnt in the previous lesson, glass. Okay, we learned that glass, or silicon dioxide, is a poor conductor of heat. We learned that you can heat it up, that the particles are near to the flame will absorb the heat, but they won't transfer that heat along the bar. What will tend to happen is the glass will tend to melt and to flow around where the rod is very, very hot, but the heat won't get passed along the length of the glass rod. So why does that happen? Well, using this model of particles vibrating, what we see is that the atoms in the glass are held together in a different way. They are in fact held by what we call covalent bonds, which you'll learn more about when you do GCSE. But this means that there are larger gaps between the particles, or larger gaps between the atoms in the glass or silicon dioxide structure. Okay, the red atoms actually here are oxygen and the white ones are silicon, and as a result of that it's harder to transfer those vibrations, okay, from one atom to another. So therefore the heat doesn't flow so easily as it does in our typical metal, where the atoms are very closely packed together and the vibrations are easily passed on from one vibrating atom to its surrounding atoms. Now, this model for heat transfer in a solid, or conduction as it is known, is a rather simplistic model. That is, the idea of heat being transferred simply by atoms vibrating and knocking on those vibrations to those around it. Although saying that, this model is perfectly adequate to explain conduction at both GCSE and IGCSE physics levels. However, I would like to point out there's a far better model which uses the idea of free electrons to transfer heat. Now, This is something that you should be familiar with because you've already met these in the area of electricity. Okay, and we will do that next lesson, but let me just point out to you why we should be looking at this free electron model for the transfer of heat. Okay, so just looking at this table here, I don't want you to worry about the units here, either for thermal conductivity or electrical conductivity. Just look at the numbers, and all you've got to do is look at that here and just go down this list. And so we're going here from the best electrical conductor, which is silver, down to the worst electrical conductor on the list, which is tin. And you can see the electrical conductivity is gradually reducing. And then if you look across here to the figures for thermal conductivity, you see exactly the same thing happens. And as a general rule, in just about all cases, if a material is a good electrical conductor, it is also a good thermal conductor. So whatever mechanism is being used to transfer electrical energy along a conductor, clearly that same mechanism is being used to transfer heat as well. Okay, and we know what transfers electrical energy, and that is the free electrons that are present in the conductor. Okay, so in the next lesson we'll look at a slightly more advanced model to understand thermal conduction in a solid using the idea of free electrons. Although I will state this, that this is not necessary for your IGCSE syllabus. You're perfectly fine with the vibrating atoms particles model that we've just seen.